Before the workshop starts, we're going to show you how to navigate through the video. Below the YouTube video is the Show More button. Click the Show More button to reveal the index. You can skip to the point that you want in the video by clicking the blue time link.
Why S instead of sigma? There's a sort of a corrector there. They divide the S by n minus 1 when n is the sample size rather than n. It has to look for bias, you see, and there'll be bias in sample, and that sort of corrects it. Now, so if they mention a sample, they should be really using the S, and if they mention a population, you should be using the sigma. Okay? Now, why did we choose this approach? Well, we had guided activities. They'd make their own discovery, share, co-construction. Revision of shape center spread. Prediction was important there. Difficult to visualize the central limit theorem, but I think now between the proportions and this one, we have an idea where it came from, Strikes a balance between physical sampling and ICT. All in one wouldn't be ideal. Students come up with the mean of the sample means themselves. Okay, and it's easier to picture a confident and a hypothesis, not just a list of steps. Now, one final bit, about 10 minutes, we're just going to tie the thing together. If we got a question, how do we use the theory, in other words, to answer a question? So, in reality, we won't know the population mean. So, we won't know that. We have the sample of size, so n is equal to 30. We have x bar, which is the sample mean, is 4.5 kg, and we have s, which is 2.8 kg, I think, is it? Sorry, 2.5, sorry, yeah, 2.5, okay? Now, what can we say about the population mean? So we must now infer from the sample to the population. Okay, so we have a few hints. What do we know? What can we determine? And what links these? And on page 8 in your little booklet there, we'll have one look at that, and I'll tie this together quickly for you. Okay. Now, so the solution. Well, the first question is, make a statement about the population mean. Well, simply it's around 4.5. We know this from working with the theory, don't we? Because we saw that all the sample means were not that far away from the true one. Yeah? So it's a good estimate for that, okay? So it's around 4.5. Now, there are three spaces then, sample, population, and sample distribution there in the down, okay? Write down and sketch everything you know about each where possible. Now again, it's the where possible. And the hints, what do we know and what do we not know? What do we need to know to find what we do not know? What do I know that can be helpful? And what's similar about this problem to what I already know and what's different? So let's look now, and we look at our sample and let's fill in what we know. Okay, well, I know the mean of the sample, x bar, is 4.5. I know the sample size is 30. And I know S, the sample standard deviation, is 2.5. I can gather two things from those. The 2.5 is our best estimate for sigma, for the population standard deviation. That's the best estimate. And actually 4.5 is a pretty good estimate for the population mean. So I know that, from my theory now. Is that, we're happy enough with that? Now, so let's leave the population for the moment and let's go down to the theory, the sampling distribution of the means. And that's our central limit theorem here. So let's look at this, the bottom one. The sample is large enough to say that the sampling distribution of the means is normal. Now, a large sample, lads, is 30 or more, so we have 30 in ours, so that's okay. So we can say the sampling distribution of the sample means is normal. Okay? Now, we can say that. Now, the standard deviation of the sampling distribution of the means is known as the standard error, and it is sigma over root n. And it's sigma over root n. Remember, we saw that they got narrower when you divided, remember that? No, but we don't know sigma, so that will approximately be s over root n, which of course is 2.5 divided by the square root of 30. So I can actually get that standard deviation of that fella there. And it's 0.4564. And that's equal to 0.4564. Does that make sense now? Now what I'll do here, look, is I will draw then, look, okay, it's a normal, in there is our mu. And I know the standard deviation of this distribution is sigma over root n, so actually it's 0.45. If I go 2 standard deviations either side of this, I know I should capture approximately 95% of the data, isn't that right? So therefore, now I'm not actually using 2 because it's a Z tables, it'll be 1.96. So I'm actually looking at here, look, mu, we'll say this would be mu plus 1.96 sigma over root n, and down here would be mu minus 1.96 times sigma over root n. And between those two lines, or those two limits, here and here, I know that I'll have 95% of the data. And of that, the data is the sample means. 95% of them will lie in there. Does that make sense now for us? Okay? Are we happy enough with that? 95% of them lie in there. Okay? So when all that was worked out, it was 0.9. So basically, I could build around 4.5 plus or minus. You see, I'm actually building around this x bar plus or minus 1.96 times sigma over root n. And I'm creating a limit around my best estimate. And that sort of runs from, what did I say, 3.6 to 5.4. So there's 3.6 and 5.4 kg. You know, I've done that in the second one. When I multiply this now by 1.96, I get 0.9. Okay, I have it done down here, look, in this one, for the 95%. Does that make sense for us now? Okay? Now, so what can I say? The population mean is around that. I am 95% confident that the population mean is between 3.6 and 5.4 kg. I am 95% confident that it's in there. Okay? Now, going back to my one again, I could try and build this sampling distribution, center it at 4.5, look, or I could center it at maybe 3.9 or something, or 3.8, or it could be centered at 5 point something, you know. So I don't know where to put this one here. All I know is that somewhere between 3.65, we know that 95% of them should be captured in there. That's all I know, okay? And, you know, and I suppose we're getting the idea there that some of them will be captured and some won't, you know, the 5%. Now, this is the crucial slide for understanding. So, you have this one done out before, so I'll just go back and you might have to, you know, I'll just say, now look at our population, our large sample, and all the sample means. So, when we take our large sample, we know that x bar is our best estimate for mu. Yep. And we know the center of the population is at mu. That's a population parameter. And we know that the center, if I took all the sample means, and this is theory really, the center there would be mu also. And it would be written as mu x bar. It would be the mean of all the sample means would have to be the population mean. Does that make sense? The mean of all the sample means would have to be the population. Now, so there's our center. Now let's look at our spread. S I can calculate. That's a very good estimate for sigma. S is a very good estimate for sigma. That's that. Now, what is this spread here though. The spread here is sigma divided by root n. Okay? Remember? Sigma divided by root n. Now, we're left with the shape. Okay? The shape now here. The population, the large sample, I don't really care, because that will vary from sample to sample. So I'm not interested in that. The population, I don't know. So that won't interest me. Okay? Because it doesn't really matter what shape this is once my sample size is large and anything over 30. I know that down here, all the sample means, and this is the crucial one, this will have to be normal. And of course, if that will be normal, and even lads, if I start off with a uniform distribution and get the means, and I'll always end up with the sampling distribution being normal. Okay? Now, there's one other little link back up. What is this made up of? That normal distribution. That is made up of all the sample means that I could possibly get. And of course, because that's normal, in fact, this is one of them, look. And I know that 95% of these fellas will be within 1.96 standard deviations of mu. Like, that's the link there. That 1.96 of them will be within, 95% of them will be within 1.96 standard deviations of mu, or standard errors. Okay? And we're going from a large sample, inferring to the population, making use of the theory. And that's your central limit theorem. Is that okay for us? Yeah, okay. Now, just a few things then. I'm actually going to stop here now, so I'm not going to look at a hypothesis test or anything in this. I'm just going to scroll forward. Now, you could show again, you see, look, the same as I did with proportions. Look, that one of them will miss out in 20, so 95% like will be captured and one won't. You know, that fellow was outside, it missed it. So that's just a summary. And that was then a hypothesis testing. They were kind of questions, but they'll be up on the website for you, okay? And so confidence interval for proportions, analysing the relation and using the relationship. Here we got a question, look, with a skewed one, and they asked us, they said, look, in a computer simulation, random samples of size 200 are repeatedly selected from this population, and the mean of each sample is recorded. 1,000 such sample means are recorded. Describe the expected distribution of these sample means. Your description should refer to the shape of the distribution and to its mean and standard deviation. It's just what we did. You know, that's what we did there. And so look, the distribution will be narrow, large amount of samples, normal distribution centered around X bar, and with a standard deviation, look, of 10.4 divided by the square root of n, that one there. And you just draw a narrow type of one there for that. That's where we got a sample question. And there's a modular course where they really do all that stuff. There's 2 nights of it, 4 nights altogether. They do functions and calculus as well. And that might be advertised here again over the next week or so, that one. So thanks. Now, a bit of a rush there on that. Is that okay for us? Now, you'll be glad that's over, I suppose. Now, we're going to look at problem solving, and we have some nice activities now for you. In fact, we even have a video. Yeah, so we're coming up in the world. Now, so here we have, yes, now, teachers, we spend an awful lot of time worrying about what we're going to tell students and thinking about their what experiences. So we're going to look now at maybe where we might be able to introduce a little bit of problem solving and cover some of the learning outcomes from the syllabus, like in the meantime. Okay? Now, the Chief Inspector report, emphasised teaching for understanding, mathematical rigour very important, students working together, making connections, challenging the more able students and justifying the reasoning. And the teachers there in the lesson study one found that the justification was difficult for them because they didn't, they probably hadn't enough practice at it. Now, if you watch this video and guess the question I'm going to ask, it couldn't be simpler. Okay, now, of course, the question was, now we go back to it. Thing seems to be, I got a new mouse and it seems to be firing the thing all over the place, so yeah. Now, what are the questions you're going to ask, you think? Like, what was the number of his car that he drove into the centre in or something? No? What time was it on the clock, or what sort of shirt was he wearing, wasn't it? So what do you think was he doing with those little post-its? He was covering, wasn't he? Yeah. So what question could we ask? Maybe how many post-its to cover the front or something, or the side? Yeah, or something like that, now, I want you to guess to cover all sides of the file cabinet apart from the base, and you're allowed to get it wrong. So you could work there as two groups maybe and come up with a ballpark figure, that you're covering the front, the back, the two sides and the top. Now, you saw what he was doing. Now, you're allowed to be wrong in this occasion. Okay? Now I put some samples that came up other days on the flip chart. Now, of course, they could be put to put you off as well. These samples. These were answers from other days. They're all wrong. Yes. Okay, now. So now we have, why are we estimating? Because questions have come where we have to use estimation. Remember the one with the silo, and they said the average man, and you had to guess his height, and then everything built up from that. That was an ordinary leaving cert one. Then you had the clinometer and the two guys going up the slope measuring the pylon, the height of the pylon, and you had 10 degrees, and that was it. And you had to come up with measurements for angles and lengths and things, okay? So we'll look at that now, and so what information would be useful to know? Like, there must be things that we might like to know. So what would have been very useful there now? Some dimensions, I suppose, isn't it? Yeah, so definitely it would like to know the dimensions of the cabinet and the dimensions of the post-it maybe. Like, then if we had those, we were away. Now, so if we start with the post-it and we have to estimate again, and usually I find something like this works really well. If you say to them, do you think would it be that big? And they might say, I don't think so. And say, maybe what about that? And say, is that still a bit big for a post-it? And maybe what about that? And they might say yes, and then you're reading maybe 6 centimeters or something. So maybe that might be, sometimes when they can, if you can guide them in, and they all have a ruler, it's always a good idea to them say, look, would you think it would be that big, and then go halfways and half again, to get an idea. So we might say in around 6-ish, yeah? 6 centimeters. So we'll see. Well, in fact, it was 7.618. So there's our first one we need to know, 7.618, and it's square, okay? Now, we obviously were paying attention to the guy, and we see how tall he was, you see, maybe, or And it would be useful if we had a cabinet like that height in the room. We could stand near it, you know. So now we need to look at those. So we have a hint there on that. So there's a hint there. Certainly we knew 12 of these fellas went across. So we could actually work up from that. And of course the thing is, that seems to be a side he put them on, look. Okay. So if you go 12 times 7, that's 84. So that's probably going up towards 90. Yeah. So is there a kind of a relationship, even looking at the cabinet here, like the locker, like is that roughly half this, you say? You know, so you could work your way through. So maybe if you got one of those, you'd be able to work. Now, what about the height, do you think? Roughly around the man's size? Yeah? Yeah, so in fact it was 183. Height, yes, centimeters, yeah? Now, what about the width now, or the width there? See, would it be half it? Yeah, in around half it, yeah? Well, of course, if you went 12 sevens, like, you know, you'd get up. Now, what about the depth? The depth, again, that seems to be about half this, you say, yeah? Yeah, 46, yeah. Now, so we have a 183, a 91, and a 46, and a 6.718. So now we'll say, do the real math now, so work out exactly. You can do it in the calculator. So what you have now is the following. You have your cabinet here. So that's 183, 91, 46, and then you have 7.618. They're all centimeters now. So fill them in now and give me the exact answer, and we'll see who was right. Okay, so we'll have a look where you're right. We were out by one. Okay, now we were out by one. So, were you right? And of course the problem arose here where for the handles, so there's the one, like, you know, 935, yep? So you did well. Your estimate was the same, was it? Okay, now, further questions we could ask. Like, for instance, if the width of the cabinet was doubled, how many more post-its would be needed? I think you'll double everything, you know? If the height was doubled, how many more post-its? If the depth was doubled, how many more post-its? How long would it take to cover if it took 40 seconds for every 5 post-its? And then an open-ended question for the person who's, I'm finished, like, and I'm bored. If you had 1 million post-its, what kind of cabinet would you cover? That forces them to think. Yeah. You know, so so there's a nice bit there, and there's everybody can engage with that, can't they? Like, from the beginning. Why? It's engaging. It covers the learning outcomes 3.4, where estimation is important. It's accessible to most abilities, realistic, you can challenging extension questions, really, you can differentiate in the class there. And the guy involved, look, is Andrew Stadel, S-T-A-D-L, Andrew Stadel, and he does an awful lot of work on number theory, and he has some nice stuff up on his thing, okay? So Andrew Stadel is his name, okay? Now, that was the intro. We have now the more challenging bit for you. Okay? We'll be able to focus down on the work you see in each group after for the next part. Okay, now the only way to learn mathematics is to do mathematics. Okay, so now we have our whiteboards, or no, you should still have hopefully 3 pages untouched near the end, yes? Now, so you have rulers and things and pencils, and if you haven't, there are pencils, more of them here. And what I want you to do is to draw a square on the dotted grid paper encompassing exactly 25 square units, and all vertices must be on a grid point. So if I start there, the end must be on a grid point here and on a grid point, okay? That seems straightforward enough. So that's our first channel. That's the one to warm up. Now, we need to think back maybe to this morning. Challenge 2. Now, draw a square on the same dotted grid paper encompassing exactly 29 units square, and all vertices must be on grid points as well. Now, if I'm going to begin here, well, 1, 2, 3, 4. I need another 1, 2, 3, 4. Now, and if I come up this way too, when I join those across, look, I get 5 and 2. I'll get the square root of 29 using Pythagoras. See, if I come along 5 units and go up 2 units, now I have the square root of 29. Now I must build from that. Okay? So let's try that now first. And is there some sort of a pattern that we can build along that? You drew it like that, and you're actually verifying straight away, because we can see that, look, each of those are 5, and there are 9 small ones in there, 5, 10, 15, 20, and 9, 29. We have that verified. Yeah. Is that okay? Now, and you have your one there then where you came, this idea, look, from the outside was the second one, and 49 minus 20 gave you, yeah, okay. Now, could we come up with a third one? Now, this is a kind of a dissection method again, like, could we come up with a third method that we could... And we have nice little ones there, look, showing Pythagoras, you know, with the tiles and the methods inside, you know, working with those. And they're learning resources they come from, learning resources. They're very nice. Like, well, if I open them up, you can take out the tiles and get them to fit around. And likewise, you can show there, look, that those 9 and those 16 will fit into those 25. So it's good resource for the... Now, so anybody think of a method that we might use? Now, let's go back to something like this, look, and take the large square and mark out an area of 25 and an area of 4. Okay? So we're going to look at the large one now first. So we'll take that out of it and see what's left. Now what's left here, look, are those 4 sections, look. This one, this one, this one, and this one. And they fit in with your one, of course, from the previous, look. Because when you put that, and that, you can take those 4 out and slot them in there. Well, we know we have 29 here. and when we take it away from those 4 are taken away from the overall, you're left with 29. So if I put the 4 around it there like that and take it away from this must be 29. Bit like that proof of Pythagoras that used to be there, you know, in that. Now, how else could we extend this lesson? Like, we want to get more from it than that. Supposing we put, if I just go back a little bit to the first one a bit there. Just one sec now. Now, if I just went to that, supposing I put a coordinate axis on that. Now, look at all the revision I can do from this. If I put a coordinate axis, say, even there and there, so that'll be 0, 0, 1, 2, 3, 4, 5, minus 2, 7, 1, 2, 3, and then I'd come out here, 2, 1, 2, 3, 2, 5. Now, I can use then slopes and show that the opposite sides are parallel. I can use perpendicular slopes. I can use the distance formula to get, so I can use coordinate geometry, you know, to show that. So I have my revision done while I'm doing this question in the coordinate geometry. Does that make sense? That's how you might shorten some of your work. Rather than looking for new sets of points, just put a coordinate axis, because if you remember one of the questions we got, a geometry question, and in the next section they superimposed a coordinate axis on it and it became a coordinate geometry. So they tend to link those. So, and you can set the axes wherever you want to, but to try and keep many as positive as possible, if you put that one 0, 0, and get the distance from there to there, and the distances, and you get parallel lines and perpendicular, and so you can use your slopes, and you're using your slope formula. Okay, now just moving forward again from this. Okay, now the student misconception on this sort of it, that's called the tilted square, is that if I came along here and 5 and rotated it up, it would actually fall much shorter. This is a tilted square that's 5 along and 1 up kind of thing. Do you understand? It's 1, 2, 3, 4, 5 and 1. So the length of that line there is actually the square root of, what is it, 26, I suppose, the square root of 26. In that particular case. So it's not just a rotation which would rotate it up and it would fall a little bit shorter. Now, we're going a little bit further now. This is where we have the next blank page. Investigate how many separate squares, regular or tilted, which with areas of between 1 and 16 can possibly be drawn on excuse me, on dotted grid paper. Again, all vertices must be on grid points. Now, what I'm looking for here is, you look at all the sort of whole number areas now between 1 and 16, an area of 1, an area of 2, an area of 3, an area of 4. And how many of those can you actually draw? So go with the regular kind of fellas first. So can I draw a square of area 1? Can I draw a square of area 2, of 3, 4? Okay? And think a regular one. So think about that. If you work in a group, it's probably better there. So we end up, I think, with 9 of them. And they're the possible ones that could be drawn, look. Now, there is a bit of a pattern, you see, and I think you had it there, Richard, about how do you go about it, you see? Like, you know, you go around in a sort of a circular way, like 2, 1, 2, 1 or something. Yeah, you know, and once you get that, you know, they get easy. Now, everybody got the 1, 4, 9 and 16, the regular ones. Now, this we could call the 2, look, is 1 along, 1 up. Gives you 2. 2 along, 1 up will give you 5. And 3 along, 1 up will give you 10, you see. So, you know, they're called the 1 up ones. 3 along, 1 up, 2 along, 1 up, and so on. Now, we look at the 2 ups. So 2 along, 2 up gives you 8, and 2 along, 3 up will give you 13. Okay? Now, what we were saying, look, is how I could deal with one of those, look. I start here and I go 1, 2, 1, 2. Then I continue the circular motion, look, 1, 2, 1, 2, and I have this. Then I go 1, 2, 1, 2, and I'm here, and 1, 2, 1, 2, and you go around like that, you see. And it makes, you can follow, can we see that sequence? Now, so we could do all of those. Now, having drawn those, and the others are not possible finishing on grid points, we now look at, we're going to search for a pattern, you see. We're going to take it to the next level. So we're going to look at the areas, and we set up a table, and the square that has a side of 1 has an area of 1, a side of 2 has an area of 4, a side of 3 has an area of 9, a side of 4 has an area of 16. So what about a side of n? What should that be? N squared. Now, if you might have to, for some of them, 1, 4, 9 and 16, and you may have to look at the differences, and that's 3, 5 and 7, and then you get 2 and 2, and the second difference is 2, and then the coefficient of the n must be a half that, so you'll have n squared. Do you know how you check for second differences? And then if you want to, say the f of n is equal to n squared plus an plus b. We don't know what values they have yet. And if you take the f of 1 is equal to 1 squared plus a times 1 plus b, which is a plus b plus 1, and that's equal to, 1, isn't it again? Yeah, so that implies a plus b is equal to 0. Now if I get the f of 2 then, is 2 squared plus a times 2 plus b, which is 4 plus 2a plus b, and that was equal to 4. So you have 2a plus b is equal to 0. So 2a plus b is equal to 0, and a plus b is equal to 0. And when you subtract, you get a equal to 0, and then of course b is 0 as well. So your general is n squared. You know, they can do that checking if you want to just check the differences in that. Does that make sense? You know, I could have waited for one of the harder ones. I can do another one anyways. Does that okay? Now, we would expect the good students, I think, to see this, wouldn't we? You know, but you could say to them, like, can you prove to me that it is? So you could send them back to do something like this, you know, to check that they can, that it's a quadratic relationship. Okay? And of course, we can link that. We know what the graph of that looks like. You know, the x squared graph. Okay? Now, so that's the regular one there. Now, let's look at the 1 up. Now the 1 up here, so this coordinate here, look, is 1 along, 1 up. The coordinate at this point is 2 along, 1 up. The coordinates there, 3 along, 1 up, and 4 along, 1 up. Now we had those 2, 5, 10, and 17. We're just looking for a pattern here. So the 1 along, 1 up has area of 2. 2 along, 1 up has area 5. 3 along, 1 up has area 10. 4 along, 1 up has area 17. Now, what about n along, 1 up? So, can we see any pattern in that one? Like, or could we give a shot at what the general one would be? No, well, you know, 1, 2, then 2 has an area of 5, 3 along has an area of 10, 4 along has an area of 17. Right, so you're going with n squared plus 1. And again, you see, you know, which of course is what it will be. You see, you're looking at n squared plus 1. Now again, if you just wanted to check like 2, 5, 10 and 17. And like we get 3 there, 5 and 7. And when we go to the second difference, we get our 2 again. So we know then that our f of n is equal to n squared plus an plus b. Now if I get the f of 1 is 1 squared plus a times 1 plus b, which is a plus b plus 1, and that's equal to 2. So a plus b is equal to 1. And then the f of 2 is equal to 2 squared plus a times 2 plus b, which is 4 plus 2a plus b, and that's equal to 5. So we get 2a plus b equal to 1. So we solve then 2a plus b is equal to 1, and a plus b is equal to 1. So we know when we eliminate that we get a is equal to 0, and then a plus b is equal to 1, so b must be equal to 1. So it turns out to be f of n is equal to n squared plus 0 times n, so plus 1, and we have our general formula shown like to them there, you know. And it's just a bit of revision that you might like to bring in there. Does that make sense to us? Okay, now we think they'd always think then they have the pattern, like they don't know what's happening. So we go to the next one, and we'll go to the 2 ups, look. So we say to them, look, 1 along, 2 up, 2 along, 2 up, 3 along, 2 up. Okay? Now, when you go 1 along, 2 up, you get 5. Remember, that's the same as 2 along, 1 up. 2 along, 2 up was 8, 3 along, 2 up was, and then 4 along, 2 up is 20. So you're likely to get what kind of an answer now for this one? N squared plus 2, you know, given that the last one was n squared plus 1. And of course, we're going to try now to them and say, right, 1 squared plus what gives me 5? And this is another way of looking at it. 2 squared plus what gives me 8. 3 squared plus what gives me 13. So 1 squared is 1 plus 4 gives me 5. 2 squared, 4 plus 4 gives me 8. 3 squared, 9 plus 4. So now we see that the general one actually is n squared plus 4 for those. So the up bit is actually squared. Okay, does that make sense now? You know, there are different ways now, and you have all this yourself that you would approach it like, you know. You can use this, or you can sort of get them to reason it out here and what's happening. Okay? Now, so we have n squared plus 4. So now we have got some patterns. Now let's look at those and try and generalize. Okay, so the square of side 1, the regular now 1, 4, 9 was n squared. Then the 1 up was n squared plus 1. The 2 up was n squared plus 4. We'd hope now that they had latched onto it. So what would the 3 up be? N squared plus 9. And the 4 up, n squared plus 16. Okay. N squared plus 9 and n squared plus 16. Okay. Does that make sense now for us? Now, we're looking now at this and we say, right, could we go a bit further and move this one on to a sort of a general version, you know? And if we went, for instance, A along, B up. So if we went A here and B up, well, we know this is the square root of A squared plus B squared. So now we know that the area of this must be A squared plus B squared. The sum of 2 squares. Okay. Okay, and what does the formula for the area of tilted squares look like? Well, here it is, and it's a proof in form, and we get A squared plus B squared. Okay, so we're A along, B up. Now, nice question coming up. Draw a tilted square of area 25. You already drew a regular one of area 25. Now could we draw a tilted one of area 25? Now, here we go, look. If we go here, 3 down and 4 along, 3, 4, 3, 4, we can draw it. And we're now beginning to look like 3, 4 and 5 go together to form the Pythagorean triplet. So we're now linking across. And we had Pythagoras in the morning. So now, so we can get a 1 of 25. Now, here's a nice question, look, to force us to think for a moment again. What are the areas of the next 3 squares which can be represented as both regular and tilted squares on the grid paper? Explain how you got your answer. Now, after 25, so you know, the next regular one after 25 is 36. Can there be a tilted 36? Can there be a tilted 49? Can there be a tilted 64? Can there be a tilted 81? Can there be a tilted 100? Yeah, we think about that now. We'll have a chat about it for a moment. So we'd be looking at that. So we got 100 and 169, like, you know, so we're probably okay with that. Now, just looking at the content here, lads, we could have done slopes of perpendicular and parallel lines. We didn't really focus on that, like but we could have used that there in showing that there were. We used Pythagoras quite a bit, actually. Area of a square and right angle triangles. Finding areas by dissection methods. Surds and number theory we used there. Investigating and collecting data. Searching for a pattern we were. Generalizing to a method. You know, we went along and built the thing up, and we had an attempt at a proof. And of course there was reasoning, problem solving and persevering. Reasoning, problem solving and persevering. Okay? Now, and I suppose perseverance is a big thing that they need, and we need to get some practice at this type of work if we need to fit it in somewhere, you know, for them. Okay. Now, why? It connects to other areas of the syllabus. Similar to doing real mathematics, can be adapted to all levels. Level playing pitch, entry point is accessible for all. Enjoyable for students. You're basically acting as a guide, the teacher on the side. There was a jigsaw question there on the higher level, a sample paper which was needed that kind of material. And of course we're there, look, explain finding, explore patterns and formulate conjectures, justifying conclusions and so forth. Expected value. It is difficult to make predictions, especially about the future. Yogi Berra, now he was a baseball coach and player, very famous. So, you know, and this is, look at this. Why? Why are we doing this? Well, in 1.2, concepts of probability, it says calculate expected value and understand that this does not need to be one of the outcomes. Recognize the role of expected value in decision making and explore the issue of fair games. Okay? So this is part of the ordinary Leaving Cert syllabus. Okay? So we'll go through this now, and there's some nice parts in this. Okay? And the prior knowledge is understanding the basic probability theory. Just that's all we need, basic probability. Now, on page 10 there in your booklet, there's a game called Numbers Up. Okay? Now, and it works like this. A fun fair game called Numbers Up involves rolling a single die. Here are the rules. You win the number that appears on the die in euro. 4 euros for a 4, 6 euros for a 6, and so on. So the questions now we're asking, how much did you win? And you might say 3.4. Sorry, how much did you win? Maybe 340 or 680 or whatever you won. You know, and then you divide it by 20. Okay, work out your average 20 times, that's fine. Now, when you have the value, fill in the table below. So your average and the class average. Now, does your average differ from that of the class average? Like, it's unlikely that anybody is the same as this. So we're all going to differ, aren't we? And the question is, why? Why is the class average different to your average? I suppose your average is an average of 20, isn't it? And the class average is an average of maybe 10 20s or something like that, you know? You know, so you have a greater number, like, you know, it's the average of a greater number. What do you think the class average figure represents in the context of the game? Well, in the context of the game, the class average is the average amount you would win, I suppose, if you play that game over a long period of time. Okay, that's the average amount you would win per game if you played the game over a long period of time. The average amount you would win per game if you played it over a long period of time. Now, your question says, would you pay 2 euros to play this game? And you'll probably say, well, I would. You might look at your own average though, wouldn't you, first? And if you were in and around it, you might say, you know, but you probably, you know, the students would say, oh, I would. Would you pay 3 euros to play this game? No. No, well, you might have got 290, you're saying. I don't think, but some might say they might. So now we're trying to lead them up. If you ran a numbers up game at a fun fair, how much would you charge people to explain your answer? Now the students now would be answering this like, and and they may come up with a variety of answers, like from €5. They could charge anything, couldn't they? But they have to justify it. So what would they say? What do you think would be a fair price to play this game, and why? Now, so we're looking at the idea of fairness. Now, of course, when you're dealing with students, fairness only applies one way, and that's fair to themselves, isn't it? That's not fair, because it impinges on them. So you'd be hoping that they would give you some figure, maybe somewhere between 3 and 4, right? Yep, but we would have to take whatever they gave us. And they give a reason. Now let's move on a bit and look at this idea of a fair price. So we're going to look at a 6-sided die again, a fair die, and if I roll the standard die, what is the average score I can expect? And that allows me to branch out a little bit now and look at a probability distribution table, where I deal with a random variable x, and in this case it's a discrete random variable because they're whole numbers, 1, 2, 3, 4, 5, 6. They vary only in whole numbers, so it's a discrete random variable. And of course each value, like 1, has a probability of 1 and 6 because it's a fair die, so they all have 1 and 6. Now if I ask to get the average of that, I can go back and say sigma fx over sigma f type of idea. But of course, at this stage, they should know that what happens when you add all the probabilities together, you have to get 1. So they can work it out simply by getting sigma x multiplied by its probability of x. And 1 by 1 over 6 plus 2 by 1 over 6 plus 3 by and so forth. And we get 3.5. Now, and remember, in this syllabus it said, and the average or expected value there, that average need not be one of the outcomes. And of course we see there that 3.5 is not one of the outcomes here, 1, 2, 3, 4, 5 and 6. Okay, and that's known as the expected value. So if I rolled that die often enough and took the average of hundreds of thousands of times, I would expect to get in around 3.5. Do you understand? As my average. Now, if we go back to our numbers up game, so therefore the average that I would expect if I play this game to win over a long period of time would actually be 350, isn't it? If I played that game, so our class average was actually quite close to that, on this. Does that make sense now for us? Now, so the expected value is how much money a player can expect to win now, or maybe lose in the long run on a particular bet. It's in gambling, the house, risk analysis and insurance, it's used in that. Economics, decision theory, used quite a lot there, okay? And the mean has been described as the average of what has happened, while expected value is the average of what is going to happen. So when you talk about the mean, it is what has happened. You have and what would happen is going to happen if I did it over a long period of time. Okay. Now, there's nice teaching ideas in the probability kit, and they give these spinners quite a bit. Now, let's look at it a little bit further. Mathematical expectation here. Suppose a couple decide to have 3 children. How many boys can they expect to have, assume boys and girls are equally likely? Now, I think the statistics are kind of slightly in favour of boys, aren't they? Like 50.7 or something to 49.3 or something like that. Now, we make use here, look, of the 3 diagrams. And it's a very good way of figuring out the sample space, look, because they're easily counted in boy, girl, boy, and we get our 8 different there. And we have here the 8 different, and at ordinary level and at foundation, they ask them to write out the samples, or to complete the sample space. They may start them off a bit, okay? Now, so let's put those on a table. So the random variable here again, x, and the probability of x here, you can have either 0, 1, 2, or 3 boys in a family of 3. So you could have no boy, 1, 2, or 3, and then we count the probabilities of no boy here of 1 by 1, 2, 3, and so forth. 1 over 8, 3 over 8, 3 over 8, and 1 over 8. Now we get the expected value there, and it turns out to be 1.5. So if we had families with 3 children, and if we had lots of those, on average we'd expect to have 1.5 boys. And I suppose we'd have the same then 1.5 girls, like as the average on the other. Okay? Now, fairness now or unfair. Is that a fair game? Like, so we need to look at this as part of things. So if I get its expected value there, and the expected value of x is 8, and I have a 1 in 2 chance plus 2, and I have a 1 in 2 chance. So that's 4 plus 1 is equal to 5 euros. And of course, if I pay 5 euros to play it, 5 minus 5, I end up with 0. And if the expected value is 0, when the cost is taken into account, the game is said to be fair. Okay? Now, I could also work on it like this, and work on this method. If I land on the 8 here, I would be plus 3. I'd be up 3 euros, and I have a 1 in 2 chance of getting that. If I landed on the 2, I would be down 3 euros, and I have a 1 in 2 chance in that. So that's equal to 3 over 2 minus 3 over 2, and it still ends up as 0. So that's a fair game then. Do you understand? There are 2 ways that you can look at it. Work out the expected value and then put in the cost, or include the cost as you go along. Is that okay? So a game is said to be fair if the expected value when the cost is included is 0. Okay? Now, one for you. Is that fair, do you think? If you looked at it as it's there, what would you be saying? Not really, yeah? No. So I'll just look at it in one way for you. And if I land on, say, 2 euros, I'm going to be down 3, and I have a 1 in 2 chance for that. If I land on 4 euros, I'm going to be down 1, and I have a 1 in 4 chance of landing there. If I land on 14 euros, I'm going to be plus 9, isn't it? And I have a 1 in 8 chance of landing there. And if it lands on an 8 euros, I'm going to be plus 3, and I have a 1 in 8 chance of that. So I have a minus 3 over 2 minus a quarter plus 9 over 8 plus 3 over 8. That's 12 over 8, that's 1.5. So and that'll cancel out. So minus a quarter, so minus 0.25 cent. Okay? So I would expect to lose 25 cent in that game. Yeah? Now, so I could run that game if I stood inside the counter. That's what would actually happen. I'd be losing on average 25 cent per game, so I wouldn't be there that long. Okay, so the idea is that if the stall keeper has to have it positive in his favor always. If he's to make if it's negative in his favor, he'll be closing up pretty fast. Okay, a game is said to be fair if the expected value after considering the cost is 0. If this value is positive, the game is in your favor, and if this value is negative, the game is not in your favor. So a negative value would not be in your favor. Now, Tomas and the group in Kanturk did a one for the lesson study, an interesting one. It's up on the website on expected value. Nice taking it in Skullver. You can Google it and get it. Now, final bit. Do you ever see this deal or no deal? Yeah. No, we've adapted this a little bit just to look at what we could get, and we're. Now, this should generate one here for us, yeah. What happened in some of these is like, this is it, the deal or no deal. So you have to win something. So the banker then, like, you know, has to lose, in other words. So if we get his expected value, which is 25,712, so per individual playing, that's what he expects to lose, you say, in the long run. Okay? Now, this girl was involved in it, and I'll cut it a little bit short. And she was playing along, and she accepted a deal at 17,500. But the game plays on, regardless, you see, because obviously they drag it out, like, you know. So it came down to this, look. Yeah, you know, it came down to this. She won the 250. Now, we've some nice ideas there that they can track a game at home, look. And work through. Here's a very good one. I'm working backwards, like getting the expected value, getting the banker's offer and the percentage. He always seems to offer a little bit less than half, like, and also he looks at the character of the individual. You know, there are some that you could sort of, you know, he knows by working with them. Should you buy that extended warranty? They say never. This isn't worth it at all. Now, the expected value of a random variable is the weighted average of the values that x can take on, where each possible value is weighted by its respective probability. An attempt at describing the mean of what is going to happen, and needs not be one of the outcomes, as we saw. And some of us see the world in terms of expected value. We're very different from the rest of you. Okay. And thank you very much.
Thank you.